A first-order partial derivative measures how a multivariable function changes when only one of its inputs is varied, while all other inputs are kept fixed. If we have z equals f of xy, the partial derivative with respect to x is written as partial f over partial x or f sub x. It is defined as the limit f sub x of x0, y0 equals limit as h approaches 0 of open fraction f of x0 plus h, y, 0 minus f of x0, y0 closed over h. Similarly, the derivative with respect to y is partial f over partial y equals f sub y. Think of a landscape described by z equals f of xy. F sub x tells you the slope of the hill if you walk east-west, while f sub y tells you the slope if you walk north-south. The special symbol partial, a curvy d, reminds us that we are holding the other variables constant while differentiating. Explanation: for elementary functions, the rules look just like ordinary single-variable calculus, but we treat the other variables as constants. Polynomials: if f of xy equals x cubed y squared plus 5xy, then f sub x equals 3x squared y squared plus 5y, and f sub y equals 2x cubed y plus 5x. The power rule works on the variable we are differentiating, and any factor not containing that variable is considered a constant. Exponential: for f of xy equals e to the xy, hold y constant when differentiating with respect to x. F sub x equals y e to the xy, and f sub y equals x e to the xy. Trigonometric: if f of xy equals sine of xy plus cosine y, then f sub x equals y cosine of xy, and f sub y equals x cosine of xy minus sine y. The derivative of sine is cosine, and we multiply by the derivative of the inner product xy with respect to the chosen variable. Logarithmic: for f of xy equals natural log of x squared plus y, f sub x equals 2x over x squared plus y, and f sub y equals 1 over x squared plus y. The usual rule d over dx of natural log u equals u prime over u is applied, treating the other variable as a constant. These examples show that you can reuse the familiar one-variable rules. The only new step is to remember which symbols are treated as constants. Higher-order partial derivatives are obtained by differentiating a partial derivative again. The second-order partial derivative with respect to x twice is written f sub x equals partial squared f with respect to x squared. If we first differentiate with respect to x, and then with respect to y, we get a mixed derivative denoted f sub xy equals partial squared f with respect to y partial x. Analogously, f sub yx equals partial squared f with respect to x partial y. A useful analogy is cooking a layered cake. The first derivative is like adding the first layer of frosting, changing the taste in one direction. Taking a second derivative is like adding another layer on top. If you add the layers in the opposite order, you might wonder if the final cake looks the same. That is exactly what mixed partials test. Notation tip: the order of the subscripts indicates the order of differentiation. For example, f sub xy equals partial with respect to y of partial squared f with respect to x squared. For functions of 3 or more variables, the same ideas extend, but the principle stays the same: differentiate one variable at a time, keeping the others fixed each step. Clairaut's theorem, also called Schwarz's theorem, says that if the function f of x, y has continuous second-order partial derivatives in a region, then the mixed partials are equal. F sub xy equals f sub x. The continuity requirement is crucial. It guarantees that the order of taking limits does not matter. In everyday terms, imagine you walk from point A to point B by first moving east, then north versus first north then east. If the terrain is smooth, no cliffs, the total change in elevation is the same whichever path you take. That's the equality of mixed partials. Mathematically, the condition is f must have f sub xy and f sub x defined, and both f sub xy and f sub x must be continuous around the point of interest. When these hold, you can freely interchange the order of differentiation, which simplifies many calculations, for example solving PDEs optimizing functions. The total differential gives the best linear estimate of how a function z equals f of xy changes for small changes delta x and delta y. df equals f sub x dx plus f sub y dy. where dx and dy are infinitesimal changes in x and y. Delta f is approximately f sub x of x0, y0 times delta x plus f sub y of x0, y0 times delta y. Think of a map of a hill. The tangent plane at a point gives a flat surface that locally mimics the hill. The total differential is the equation of that tangent plane. Practical use. If you know the temperature T of xy at a location and its partial derivatives, that is how fast temperature changes east-west and north-south, you can quickly estimate the temperature a few meters away without recomputing the full formula. Engineers use this to predict how a design parameter changes when dimensions are tweaked slightly. Linearization is just the first-order Taylor series for a two-variable function. Around a point x0, y0, we write f of xy approximately equals f of x0, y0 plus f sub x of x0, y0 times x minus x0 plus f sub y of x0, y0 times y minus y0. The right-hand side is exactly the total differential plus the function value at the base point. This creates a plane that touches the surface at x0, y0 and provides the best straight-line planar prediction nearby. Example, the pressure on a shallow pond can be modeled by P of xy equals 100 minus 0.5 x squared minus 0.2 y squared. At the point 2, 1, the linearization gives P approximately P of 2, 1 plus P sub x of 2, 1 times x minus 2 plus P sub y of 2, 1 times y minus 1. Computing, P of 2, 1 equals 100 minus 2 minus 0.2 equals 97.8. P sub x equals negative x, so P sub x of 2, 1 equals negative 2. P sub y equals negative 0.4y, so P sub y of 2, 1 equals negative 0.4. Thus P approximately 97.8 minus 2 times x minus 2 minus 0.4 times y minus 1. Now for a small move to 2.1, 1.05, we can estimate the pressure without plugging into the original quadratic formula. The linearization is a cornerstone for Newton's method in multiple dimensions and for sensitivity analysis in engineering. The second-order Taylor expansion adds a quadratic term that captures curvature. Around x0, y0, we have f of x, y is approximately f of x0, y0 plus f sub x delta x plus f sub y delta y plus 1/2 open bracket f sub Roman 20 delta x squared plus 2 f sub xy delta x delta y plus f sub y delta y squared close bracket plus r sub 2, where delta x equals x minus x0 and delta y equals y minus y0. The matrix H equals open bracket f sub Roman 20, f sub xy. F sub x, f sub y close bracket is called the Hessian. It encodes how the surface bends in every direction. The remainder term r sub 2 can be written in Lagrange form as r sub 2 equals 1/6 sum over I, j, k of the third partial derivative of f with respect to xi, xj, xk evaluated at xi times delta xi delta xj delta xk, where xi lies on the line segment between x0, y0 and x, y practically. If delta x and delta y are small, r sub 2 becomes negligible. And the quadratic model becomes very accurate. Real-world analogy. Imagine a thin sheet of metal slightly deformed. The linear term tells you the tilt of the sheet. The quadratic term tells you whether it bulges upward, positive curvature, or sinks downward, negative curvature. In engineering design, the second-order term predicts stress concentration more accurately than a mere tilt. Using the expansion, optimization algorithms such as Newton-Raphson compute a step delta by solving h delta equals negative gradient f, which is why the Hessian is so important. Explanation: critical points occur where the gradient, the vector of first-order partials, vanishes. F sub x of x sub 0, y sub 0 equals 0, and f sub y of x sub 0, y sub 0 equals 0. To decide whether such a point is a local minimum, maximum, or a saddle, we examine the Hessian matrix at that point. H equals the matrix with f sub Roman 20, f sub xy in the first row, f sub x, f sub y in the second row, evaluated at x sub 0, y sub 0. Compute its determinant D equals f sub Roman 20 times f sub y minus f sub xy squared. If D greater than 0 and f sub Roman 20 greater than 0, the surface is shaped like a bowl, local minimum. If D greater than 0 and f sub Roman 20 less than 0, it looks like an upside-down bowl, local maximum. If d less than 0, the surface curves up in one direction and down in another, saddle point. If d equals 0, the test is inconclusive. Higher order terms must be examined. Example: f of x comma y equals x squared plus y squared has gradient 2x, 2y. The only critical point is 0, 0. Here f sub Roman 20 equals 2, f sub y equals 2, f sub xy equals 0, so d equals 4 greater than 0 and f sub Roman 20 greater than 0, a minimum. In engineering, this test helps identify stable equilibrium positions of a mechanical system, minimum potential energy versus unstable equilibria, maximum, or points where the system can tip over, saddle. Typical exam questions fall into three categories. Short answer definition. State the meaning of partial f with respect to x, and write the total differential of f of xy. Answer expects a sentence definition, and the formula df equals f sub x dx plus f sub y dy. Computation. Given f of xy equals e to the xy, find f sub x, f sub y, f sub xx, f sub xy and evaluate them at the point 1, 0. The student differentiates step by step, using the chain rule and substitutes the point. Application problem solving. A rectangular plate has area A equals xy and cost C equals 5x squared plus 3y squared. Find the dimensions that minimize cost for a fixed area A sub 0 using Lagrange multipliers. This requires forming the gradient of C plus lambda times A sub 0 minus xy equals 0, solving the resulting system, and possibly using the second derivative test to confirm a minimum. Another common type. Linearize f of xy equals natural log of 1 plus x squared y at the point 0, 1 and estimate f of 0.1, 1.05. Students write the linear approximation and plug the small changes. These questions test the ability to recall definitions, carry out differentiation rules, and apply the concepts to engineering contexts such as optimization, error estimation, and modeling.